So thank you very much, Jakob. So I have the feeling everybody's waiting for this report. So it's finally time to present it. But before doing this, just I want to introduce myself. So my name is Martin Rissmann from Vibratec. We are a French engineering company specialized in noise, vibration, and mechanics, and we are based in Lyon. And one of our topics is our railways, and for myself, it's now more than 6 years I'm working in railway lines. The second point I want to mention before starting the presentation is I want to thank you to Pinar and the UIC Noise and Vibration Sector Group. It was really fun working with you. We had quite some good exchanges during the project, and it was really a pleasure for me to be with you in this office. Okay, the idea is today I give you in my talk a short overview of the report, and I pick out some results which are in the report because there are many different topics. So it's the idea is to make you read it if you're interested in it. So first of all, I want to discuss a bit why do trains stand still, because normally we want them to run and not to stand still. So we have two categories of trains standing still. So what we refer to stationary trains, which are basically in service, and they, for example, they stop in a station to get passengers on board, or they have to wait on a green signal. What is normally the case in this operating condition, we have all the technical components running, so the train is fully operational. The other situation is shown on the left, on your right. It's a parked train. It's usually taken out of commercial service. It's parked in a depot or at the station. It can be parked as well on a terminal of a secondary line, and it's waiting for its next service. For example, during the night, because in the night we don't have any passengers, or during the weekend where we have less passengers to transport. The difference is compared to stationary, that only some technical components are running. Example we've seen today in Juan Zapina's presentation, for example, to protect components from cold or from too much heat. Just to give you an illustration about like what's the life of a train between commercial service and park periods, we have this example here on the lower. A diagram, you can see over 1 week, this is an example from a commuter train, the different activities of this train. And if you have a low value, it's only high and low value. Your low value means this particular mode is active. For example, we have short parking periods. For example, here we have an active parking period, and then we have periods with commercial service. You can see during the week, the parking periods can be less, or can be very short, or they can be longer, for example, during the week. Just to illustrate, parking is not just like a question of a couple of minutes, and it can have different durations. Now I want to go a bit deeper into the definition, because we had a lot of discussions within the group. What is the difference between a stationary train and a parked train? Seems to be easy to define, but it's not so. What we have found is this definition on the left and the right on a diagram based on the train speed over time. So if I have a stationary train, it's like most of the time it's running, and then we have phases where it's stopped for a short period of time, and then it's running again. When we come to parking on your right side, you can see we have a longer period where the train is standing still, which we refer to parking in a general sense. But if you look deeper into that, you can see there are different subphases in parking. So you have a preparation for resting. This means, for example, the engines are switched off, the aggregates or the temperature is lowered, and so on. So there's some noise or some activity related to the preparation. Then you have the resting phase, which is basically mean the train is sleeping, having a rest. And then you go back to service and you have to prepare for service. So for example, start the engine or start to heat up the train, for example, if you're in winter conditions. So all these activities do somehow, cause noise, and we can see in detail what are the different noise sources. One thing to say, I think we all know this, so stationary noise is quite well framed by different standards and regulations. It's less the case for parked trains, so there's still a lot of work to do, and in my talk I will focus on this aspect. You find also aspects on the stationary noise in the report, but I invite you to have a look at that in the report. Let's talk a bit about the acoustic characteristics about parked trains. So what we can say in a general manner that a stationary train is generally louder than a parked train because there are more equipments running, and if they're running, they're also emitting noise. But it of course depends on the train architecture and so on. For a parked train, it becomes a bit more complicated because the noise emitting activities depend mostly on the train operating conditions. So are we in a preparation phase or in a resting phase? And it depends on the equipment itself. We have equipment that can be running continuously, for example, a fan, which is running all the time, or we have intermittent activity, for example, the compressor. And it can depend on the weather. Are we in a winter condition or in a summer condition? To illustrate this, you have one example in the diagram on your right. So it shows the sound pressure level over time. The time is approximately 2 hours. We consider a parked electrical multiple unit, and there are two acoustic indicators. For the illustration, you can have a look at the blue lines, which is the equivalent sound pressure level, and you can see you have phases with activity, so with high sound pressure levels, and phases with low activities. And if you compare the levels, you have a difference of about 15 dBA, which is quite important. Okay, so now I introduced a bit the topic. Now it's time to talk about the report. First of all, I want to present a bit the methods we used. So a central part of the report was a survey we sent to the UIC members, and according to what you told me, it was a great success. We had in total 29 contributors from 16 countries. I think it's worth to mention there are also 2 contributions outside of Europe, with Australia and Japan. And we also have contributions from the CRR and from UNIFAE. So it's not only an UIC only survey, but we have also this other point of view. Also worth to mention, in the survey, we also asked for measurement data. So 11 participants, they also provided measurement data. We have a word on that later. So now let's look at the results from this survey. So the first one is about noise complaints. So one result is written in the first line. So over the last 5 years, 45% of the participants declared that the noise complaints increased. We asked different questions about the noise complaints, which kind of complaints we have. And one question was, what is the critical rolling stock? So we have this graph on the left, which shows the criticality from 1 no issue to 5 very critical. And we can see the most critical ones are diesel multiple units and locomotives. But nevertheless, because we have so many electrical multiple units, they are also quite problematic. A second question was the reasons for noise complaints, which is shown on the right side. And we can see 4 major reasons. They can be related to HVAC and roof-mounted sources, to quite an important part. To issues with train preparation. So I think this is mostly related to some compressors, pressure valves, and motors running up. Another one is densification and missing space. So this can be more people living close to lines, but also where to put the trains. So there are more trains at the same spot. And then another point is nighttime activities, so which can be sometimes engines are running. It can be also some activities in the depot. Okay. Next, I want to address the measurement data. So we asked if there's measurement data so that we can maybe compare it and see if we can develop some noise limit values. So we did this. The message is standstill noise measurements exist, but they are difficult to compare. The reason why this is so difficult to compare that is the assessed quantities are different. So it can be sound pressure, sound power, LPF max, some equivalent level, and so on. You can have different operating points or a missing description. So it's written like the train is resting, and then it's written the train is resting during the night, but there's no clear definition. And the measurement conditions, for example, for how long it was measured, and so on. So there's data, but they're missing description. Just to show you one example, here's an example of, we took the data we have from the Netherlands and Switzerland. We did the classification on the right per train type, and we have to look at all the HVAC components. Can be a small one, big one, everything which is related to HVAC. And then we have two modes. We have the standby mode and we have the sleeping mode. And if you look, so here the quantity is sound power level. Okay, you see some differences, but the most important thing you see, you can have a dispersion up to 40 dB. So I think it's quite difficult to set any limit value on something like that. So the message is there is data, but if you really want to use it from a statistical point of view or to go towards limit values, you have to work on the quality of the data. The second aspect, this was also quite interesting. We had some data sets where the same equipment was measured on the same train, and that gave us a hint about the variability in the measurements. So for example, here it's an HVAC unit, which has been measured on this train on the right. We have the blue ones are the ones above the cabin, and there are green ones which are above the doors. And you can see there's quite some important dispersion, especially for the one above the door. So there's also a topic about the measurement conditions and how to assess uncertainties and variability. Okay, this was some aspects from the measurement side. We also had a look into the standards and regulations. We've heard some names today. You find a quite extensive comparison between the different standards in the report. Just some word about the ISO 395. So the next revision will include parking noise. The UIC noise and vibration sector sees this as a step forward. However, there's still some open points. For example, how to measure a single component, which is required, for example, as input for environmental noise measurements. Also worth to mention, some frameworks propose noise limit values, but they're different because they have different conditions. And also, one thing I want to highlight is in some countries, parking noise is not considered as railway noise, but as industrial noise. This means this has way lower limit values, so it's way more difficult to reach. Okay, now we talked a bit about all the complaints and the difficulties. Let's talk a bit about the solutions. So there's also some aspects about the solutions. The message is there are many ways to reduce parking noise. In the survey, as you can see on the right, there are basically three main measures they're working on the operational modes of the train to reduce the noise, the use of noise barriers. But noise barriers have the disadvantage that we have many roof-mounted sources and they're not effective against this. And another aspect is special parking areas, also mentioned by Martin in his presentation. And yeah, these are the three major measures. On the vehicle side, I listed some possibilities. Can be retrofit. For example, here we have one example to exchange, for example, the fresh air intake of a passenger HVAC to a more acoustically optimized design, but also silencers and encapsulation and so on. Another opportunity is to work on software to optimize the operating mode. For example, we had the example of the fan speed. And generally, we can say if we optimize the energy consumption, we usually also reduce the noise. So this is somehow a win-and-win situation. So we also see now, or in the report, we observed that noise reduction is not always easy, but it requires cooperation between the different stakeholders. And I think we've seen today that everybody agrees on this point, and this event is one way to work in this. We have to consider costs, modifications, homologation in the entire process. It's not just like reducing noise is only an acoustic issue. It can be also touch other topics. Nevertheless, we think there are two simple measures which are identified. First one is to check the correct application of the required standstill mode. According to the feedback we had, there's the train which has a really silent parking mode, but it's not really activated when the train is parked. So there can be some work done, for example, also by team managers to control this or to motivate people to really be aware about the issue. And the second point is more about local authorities on two aspects. It's important to raise awareness about this problem that the train which is not running in part is also a noise issue. It has an impact on land use planning, so more houses are being built close to railway lines. And the second aspect is in some countries, for example, Germany, trains are ordered by regional authorities. And those people are not always aware about these issues because it's, let's say, a relatively new thing to do so. So the people are not trained or aware of the problem. Okay, and now it's time to summarize my presentation and the work we have done. So I think further work is needed. I think that's clear for everyone. Decreasing railway noise is still a top priority for UIC's noise and vibration sector. Even if there is the wish to have noise limits in the TSI, we are not ready yet. So this is still some work to do. But what we have done in the report, we give you a critical analysis of the current state with a large variety of topics going from the complaints to the technical solutions, mitigation solutions, to the regulatory frameworks and so on. So there's a lot of stuff to see. We also saw that there were sometimes diverging opinions between stakeholders. For example, we have this problem that infrastructure managers have to deal with environmental noise limits, but then they get some rolling stock from the rolling stock manufacturers or the operators. And on the manufacturer side, at least they need clear and simple homologation procedures. Last word on noise limit values. So agreement has been found that at least a common assessment procedure, including train operating modes, is required. And it could be useful in order to have noise limit values create a common shared database with more reliable data than I've shown in my presentation, to define in the end feasible but also incentive noise limit values. And with that, I'm done for now, and I'm open for discussion. Thank you.
Okay.